Hello, my name is Sean McGrath from the University of Limerick. Today I would like to present a paper on disruptive computing technologies and the influence of 5G, AI and machine learning on edge to core to cloud. This paper focuses on the challenges in computing and networking architectures driven by the emergence of 5G and artificial intelligence and machine learning. It is important to realize that these disruptive technologies will radically reshape computing and networking in the future in how users develop access and consume content and data. It can be argued that these trends will generate revolutionary rather than evolutionary change in the landscape of networking and computing. The evolution of computing, like that of wireless technology, can be broadly categorized in waves of events. The first wave started with mainframe computing that served numerous terminal client devices, which we consider or know as cloud client-server model. The architectures were based on discrete designs from the CPU, memory, IoT controllers and connectivity. Advances in silicon designs by companies like Intel and AMD and others coupled with Microsoft's DOS and later Windows OS provided a second wave, which was personal computing. This PC model provided standalone computing capabilities with the ability to share data and content using Ethernet standard. Progressive advances in CPU, memory and storage and networking, etc. allowed PC computing into mainstream usage. The third wave was essentially access to the internet, which provided a global network of connectivity for voice, video and data. Wave 4 provided mobility for the internet world, allowing communications anywhere, anytime, any place. And cloud computing provided a means of storage, but really provided a client-server model on a global scale. The transition and expansion in features and capabilities with each computing wave was dependent on key technologies, trends, and breakthrough innovation across all aspects of computer architecture. Innovation was discipline-centric, and while there were interdependencies, they did not always advance at the same pace. The general engine for transforming data into information has been continuous with the development of CPU and the modern standard, which was x86. One should note that ARM processor is one of the most popular CPUs of all time. ARM owes this success largely to the popularity in smartphone and other embedded systems. ARM is also beginning to gain some foothold in the areas of advanced accelerators. Not all waves of evolution occur at the same pace or have the same influence. The current wave we're in of AI and data analytics appears to be the biggest and will have the most profound effect on humanity, both in positive and negative ways. The introduction of wireless Ethernet or Wi-Fi was a disruptive technology that accelerated mobile PC computing initially into the enterprise and later to customer use. The evolution of wired and wireless data rates standards is both an outcome and a result of consistent innovations in PC and mobile computing architectures. In parallel to the wired and wireless Ethernet, network standards in cellular industry changed how we communicate in the world. The 5G standard, which was launched in 2020, will bring transformational change to traditional closed telcos and service provider network architectures. 5G will be the first true end-to-end software-defined network and core architecture using open standard-based x86 server hardware, software-defined storage, and network coupled with virtualization, which will bring new usage models, business, and innovation across all aspects of consumer, commercial, and enterprise markets. 5G will accelerate the integration of systems, devices, and cloud, and will enable new compute and networking use case in a service delivery model. The availability of Wi-Fi in addition to 5G, Bluetooth, and Ethernet will result in an always connected, always available computing features for users. The fusion of these connectivity options used in an integrated way will drive new innovation and performance features and applications for access to data and content. Mission critical applications like telemedicine, factory automation, and autonomous driving. Access to data will be based on policies, user profiles, location, and mission critical applications. This will drive a transition from the centralized cloud and data center models to a distributed edge compute model. The addition and use of artificial intelligence and machine learning algorithms on these new computing models, enabled by faster and more capable networks like 5G for mobile computing and Ethernet over fiber in data centers, are driving disruptive changes in computing models from the client to the core and cloud. The emergence of 5G is an inflection point that will have a transformational impact on computing and a sense of IT readiness and support. This will drive and enable new ways to access data and content using key attributes and features of 5G, including low latency, bandwidth, quality of service, and network slicing support. This is leading to new computing models based on service delivery and edge computing. Imagine augmenting client computing with cloud resources over 5G. So in addition to using cloud core compute resources, additional on-demand cloud compute resources can be applied based on user profiles, service agreements, and applications. Over the past several years, there has been a growing interest in the use of accelerators to improve data analytics on more and more of the compute ecosystem. Traditionally, they have been used on servers. The use of accelerators and AI or machine learning is now appearing on client and edge devices, network and storage platforms. It started with GPUs to accelerate AI and machine learning and is now growing to include FPGAs, smart NICs, and embedded accelerators across many devices types and other low power embedded platforms. With the exponential growth of data, an increasing number of IoT devices at the edge, and each industry growing through digital transformation, the future of computing is driven by the need to process data cost effectively, maximize business value, and deliver a return on investment. This next decade will be referred to as the data decade. Edge solutions are defined by use case, environment, industry, business function, and technology requirements such as scale, system performance, latency, security, privacy, regulatory, network resource availability, and cost. The architectural transition to edge computing is driven by 5G based on advantages in latency, bandwidth, and capacity. Edge computing is not an extension of cloud. Instead, the transition and movement of computing resources, network, storage, and analytics closer to the source of where the data is generated. As PCs begin shipping with integrated cellular connectivity, joining the billions of smartphones and IoT devices, the management and adaptability of 5G will only be possible with automation. Edge computing architectures are emerging with compute infrastructure and applications distributed across edge to cloud. This trend will lead to the emergence of a range of computing architectures that are optimized along different vectors. Massive parallel floating point compute capability in the data centers to train complex neural network models where power is of no concern, to highly power efficient devices that can infer the deployment of neural networks models at the edge. The growth in data processing has led to the use of dedicated accelerators for artificial intelligence, machine learning, and deep learning workloads. These accelerators perform parallel computing and faster execution of AI jobs compared to traditional CPU architectures. They provide dedicated support for efficient execution of matrix mathematics, which dominates machine learning, deep learning workloads. Multiple numeric precision modes beyond what is available in CPU are available to massively speed up a broad spectrum of AI applications. By exploring what AI, machine learning, and accelerators will play a pivotal role as computing, networking, and data storage gets highly distributed from edge to data centers to cloud. This technology plays a key role in the rollout of 5G and associated services at every stage of the compute spectrum. The architecture transition to edge computing is driven by 5G, based on advantages in, as we've previously said, latency, bandwidth, and capacity. IoT is driving service class computing to move closer to end devices. Companies of all sizes are undergoing digital transformation to automate their operations and better serve their customers. This is resulting in hybrid and multi-cloud deployment closer to their end users, their customers, their employees, or devices. One of the key aspects when we examine here is that it's not edge to cloud. There is a constant transition. And in the middle of that is the network, which actually transports the information or the data. So the difficulty will be the scale in terms of how we make decisions here and where we make decisions. So the characteristics that we define in terms of where we put the power, where the latency effects between edge and cloud, or what bandwidth is available, is not linear between edge and cloud. So therefore, when we examine these future architectures, we need to understand how decisions in an optimum way will be made in a dynamic basis, because any decisions you make will vary with time. And as the networks scale, trying to provide this optimization is going to be a critical factor for future networks and for future architectures. Thank you very much.